Welcome to another part of the satellite reception series. Last time we looked at the basic working principle of a dish reflector, and in this video I want to focus on the other major part of a standard satellite receiver antenna. That of course is the LNB, and we'll also see how it can be connected to an SDR receiver. LNB stands for Low Noise Block Down Converter, and it refers to a device that takes in a wide range of radio frequencies, the block, and converts them down to lower intermediary frequencies. The low noise part simply means that the overall noise figure of the LNB is low enough to not severely impact the signals it is receiving. This differentiates it from comparatively noisy converters, such as the ones used in some Doppler radars. Sometimes you will also see it being referred to as the LNBF, which is a term that specifies an LNB with an integrated feed horn or waveguide antenna. In this video I will only be focusing on a universal Ku-band LNB like the ones largely used in Europe. I do however have a cheap C-band LNB I bought from the US, so we can expect that to appear in future videos. For now, let's take a look at the LNB in question. This is quite literally the cheapest Ku-band LNB available for sale in this country brand new, and it only set me back around €4/$ in late 2022. To learn what kind of frequencies we will be able to receive with it, we will need to know a few of its parameters. First is the input radio frequency, or RF range, which is specified at the back of the box as being 10.7 to 12.7 GHz. The other is the local oscillator value, or the LO, which isn't mentioned on the box, but as this is a universal Ku-band LNB, the default value will be the standard 9.75 GHz. When the LO is lower than the specified RF, it means that the LNB is using normal high-side mixing. This effectively modifies the range of the receiver connected to the LNB by shifting all of it up by the LO value. In case of an RTL SDR V3, which normally receives between 25 and 1766 MHz, its range modified by the 9.75 GHz local oscillator of this LNB becomes 9775 to 11516 MHz. As we have seen before, the LNB is officially only rated to go down to 10700 MHz, however its filters and waveguide are usually wideband enough to allow reception even in the 3 cm amateur radio band, which starts at 10,450 MHz. Before we can start receiving anything, we have to supply power to the LNB. This is done by sending direct current to it from the receiver side over the coaxial cable. Some SDRs are equipped with a circuit that does exactly that, called the bias T, however those are usually limited to 4.5 volts and not very high currents, whereas a standard Ku-band LNB expects either 13 or 18 volts. This means that we have to completely disregard the built-in SDR bias Ts and instead use an external one. These are luckily quite simple and cheap components, as the most basic form of a bias T consists of just a single inductor and a single capacitor. This is a bias T I bought a while back. As you can see, it has 3 connectors. One for RF only, which is where the SDR will go, one for DC only, where the supply voltage is applied, and one for combined RF and DC, where the LNB is connected. If I open it up, you can see that the PCB is comically sparse, the most prominent component being the single inductor joined by 2 tiny SMD capacitors, one on each side. You can buy these at any store that sells equipment for terrestrial TV reception, as they are often used to power amplifiers inside TV antennas. You may get one with a 12-volt power adapter already included, which should work fine to power Ku-band LNBs despite them technically requiring 13 volts. If, like me, you exclusively use your SDR outside without easy access to a wall outlet to plug an adapter in, you can turn the 5-volt supply from a laptop USB port into 13 volts using a cheap DC to DC step-up converter. To connect my LNBs, I made this thing, which essentially just combines the step-up converter and the bias T into one box. It also allows for quick switching between 13 and 18 volt supply, which is what signals the LNB to use either vertical or horizontal polarization. There are also some other functions that I will talk about in a different video, so for now I will only keep it in a simple 13 volt supply configuration. Be very careful when connecting any direct current supply to a setup with an SDR. The RF only connector of the bias T has a capacitor which blocks any direct current from entering and subsequently damaging the receiver, so you can safely power the LNB at these voltages, but it will not protect you if you connect the bias T in reverse, which is a mistake that can happen easily. LNBs usually have a very high gain amplifier on the IF output, which means that it may be advisable to use an attenuator when connecting it to an SDR. I'm going to use a 16 dB attenuator, as that is the only one I have, and put it on the RF port of the bias T, so the direct current isn't going through it. I will however mention that up until now I pretty much never used it and haven't experienced any issues, but I cannot guarantee that all LNBs will be the same. Now I hook up the SDR with a short piece of coax and an F to SMA adapter, plug in the USB power cord, connect the RFDC port with a longer coax to the LNB mounted on my 80 cm offset dish, and we are ready to receive. When the LNB is powered up, which is conveniently indicated by the LED this one has, you should see a significant increase in the noise floor level in your SDR software. If that is not the case, make sure your gain isn't set too low, although the IF amplifier of an LNB would usually power through even a 0 dB gain on the SDR. Another useful setting that most SDR software offers is a local oscillator frequency definition exactly for a case like this. In SDR Sharp it is the shift setting. After enabling it and inputting 9.75 GHz, the tuner frequency will be automatically recalculated for you. For example, if you want to tune your SDR to 11 GHz in this setup, you would need to subtract 9.75 GHz from 11 GHz to get 1.25 GHz and input that into SDR Sharp. When the shift is configured properly, you can directly input 11 GHz and SDR Sharp will do the IF calculation behind the scenes. This will also ensure that file names of any audio or baseband recordings you might make will reflect the real radio frequency and not the intermediary frequency. Staying at 11 GHz, which is inside the LNB's rated frequency range, you should be able to notice the noise floor level changing as you aim the dish around, especially increasing as you aim at the ground. This is the LNB picking up RF noise reflected from the sun. Aiming directly at the sun will produce a similar, stronger effect. In terms of artificial sources, Ku-band TV satellites are so numerous and omnipresent that simply aiming the dish at any random point in geostationary orbit will result in many signals appearing on the spectrum. These usually tend to be very wide, even over 20 MHz in bandwidth, so an RTL SDR v3 which can only sample around 2.5 MHz would also perceive those only as an increase in the overall noise floor level. With a bit of searching though, you will eventually uncover some narrowband transmission. But if you don't want to be searching blindly, you can go to a website which lists TV satellite beacon frequencies. These beacons are different from the standard data transponders, as they are usually very narrow and very strong, low-rate data streams with a carrier in the center. The beacons are scattered all across the Ku band, though there do appear to be some portions of the band where they are more common. Searching for the beacon frequencies of SDR3B, for example, which is a satellite that the vast majority of the local TV receivers utilize, I can find the following. Since the RTL SDR v3 with the 9.75 GHz local oscillator maxes out at 11,560 MHz, I should be able to receive the two lower ones. The H after the frequency signifies that these use horizontal polarization, which means I either have to supply the LNB 18 volts to switch it into this polarization, or if I didn't have my switched bias T, I could also just physically rotate the LNB 90 degrees in its clamp. At this point I also want to mention the LNB skew. This is a certain correction angle that you have to apply to the LNB based on the satellite you're aiming at. Depending on how far from the equator you are located and what azimuth angle there is between you and the target satellite, you need to rotate the LNB accordingly. As a rule of thumb though, this isn't very important, as long as you receive satellites that are relatively high above the horizon. There are online calculators that tell you what skew angle should be used based on your and the satellite's positions, but you can also tune it manually by rotating the LNB after aiming at the satellite and seeing at what position the signal becomes strongest. So, with this knowledge, let's search for SDR3B on 11,446.25 MHz horizontal. And eventually we do get something that resembles the beacon, albeit at a slightly different frequency than we expect. This is a quote-unquote issue with all LNBs like this, as none of them will have the LO frequency precisely at 9.75 GHz. While their stability and precision did get better, especially after most LNBs transitioned from old dielectric oscillators to new PLL ones, things like temperature change will still result in the LO frequency slowly drifting around its rated value. This generally isn't an issue for satellite TV receivers, as they work with massive bandwidths of up to couple dozen megahertz, where any drift like this can pretty much be ignored. But when we connect the LNB to an SDR and look at narrower signals like this, it becomes more apparent. Speaking of narrow signals, if you remember earlier, I mentioned that a Ku-band LNB will still work around 10,450 MHz in the 3 cm amateur radio band. If you do have any operators or beacons nearby, you can try to receive them. But what I want to briefly mention is the SDR2 communications satellite. This is a satellite launched in 2018, providing television and data services to the Middle East. This may not sound very remarkable, as there are countless other satellites doing the same, but it is the secondary payload on this satellite that stands out. SDR2, alongside its normal broadcasting hardware, also carries an amateur radio transponder, which just so happens to transmit on the 3 cm band and can be received even with an LNB like this. But as you have likely guessed already, that will be a topic for a future video. With the dish antenna and the LNB now being covered, the amateur satellite reception series can once again start focusing on amateur satellite reception. I will also be trying to make more shorter videos like this one instead of the long and boring format used in the APT and LRPT videos which pretty much nobody watched. And that is going to be all for now. As always, thank you for watching, subscribe if you don't want to miss future topics, and I'll see you next time.